Hello, everybody. My name is Aidan Passmore, and I'll be covering part one of Project 5. Part one covers insulators, semiconductors, and conductors, where I'll be describing them as if it is a 7-year-old woman on the other side. Insulators are pretty simple. Insulators resist electricity from flowing through them, such as rubber is a very good example of an insulator. And due to insulators' low conductivity, it means that they are less likely to be struck by lightning, as lightning follows the path of least resistance to the ground. So, since rubber resists electricity, it's going to be harder for the lightning to go through rubber and then to the ground than it is for the lightning to go through something like a tree. This is where the saying of the best place to be during a thunderstorm is in your car because of the rubber on the wheels making it resistant to electricity. Semiconductors are a bit harder to explain. They act kind of as a middle ground between a conductor and a resistor, where they can act as both depending on the situation. A semiconductor needs external energy or like heat to be able to become a conductor, where in its base state it would be more of a resistor. This is due to intermolecular forces inside, but that's a little too complex for this. But semiconductors act as a middle ground where they can be conductors in an excited state or they're resistors in a basic state. Conductors are the opposite of resistors. They allow for electricity to flow through them easily with little to no resistance. Metals are possibly the most common example of a conductor, such as like aluminum, steel, gold, copper, which is used a lot for wiring and other electrical duties. And then other sources such as salt water can be known as conductors due to the ionic bonds that are dispersed throughout it, but that's a little more complex. But the main conductors that you see are gold, silver, and copper, which are used for wiring, and is part of the reason why those metals are so expensive nowadays. In part two, I will be explaining what the three primary bonds are: van der Waals interactions, hydrogen bonds, energy bands, and band gap theory, along with how our experiments showed why resistance equals resistivity times length over cross-sectional area. The three primary bonds are ionic bonds, covalent bonds, and metallic bonds. Ionic bonds are simply where one electron has a higher negative charge, while another one has a higher positive charge. So the one with the higher negative charge strips an electron or two, depending on the amount, from the one with the higher positive charge, therefore bonding them together. Covalent bonds are where two electrons with similar electronegativities or charges share atoms to form one full shell. These can be one or more, so like water is a very common example of a covalent bond, where the two hydrogen atoms share electrons with the one oxygen atom to fill the shell. And then metallic bonds are the last one, where the networks between all of them form, you could say, a network or a sea, which just allows for electricity to flow very evenly throughout. Van der Waals interactions and hydrogen bonds. So these are both intermolecular forces, and they only apply to molecules or atoms not bonded together. Van der Waals interactions are weak forces which draw molecules or atoms together or push them apart, depending on the charge. So two molecules of the same charge are going to repel each other, and two molecules of opposite charge are going to attract on an intermolecular level, where hydrogen bonds are still relatively weak, but they're stronger intermolecular forces due to hydrogen being present, and that is bonded with a high electronegative atom, which is oxygen, nitrogen, and oh my goodness, fluorine. Water is the most common example of hydrogen bonds, and this leads to water having so many interesting traits that you don't see in other ones, such as the high specific heat, and then a lot of the surface tension stuff is it's not typical of normal liquids. Band gap theory, or electron band gaps. This shows that electrons have different energy levels. These energy levels determine the conductivity, and then that is due to if the last energy level is full, that means that it is going to be more likely to be a resistor. However, if the band gap is small, which is the gap between the two energy levels or how much energy is needed for an electron to reach the next gap or the next band, it may be a semiconductor if it's small. A large gap makes an insulator or a resistor, and then a unfilled band gap means that it is going to be a conductor due to the electrons being able to flow naturally. So why does the formula R equals P times L over A work? This shows that resistance equals resistivity of a material multiplied by the length over the cross-sectional area. This was clearly shown by the example in lab where we had the big bar where you moved across and you would see the distance and resistivity just as you went farther across, and it increased in a more linear fashion. This is because the cross-sectional area remained the same and you're just increasing the length, which would cause a linear change in the resistance. And then this is also shown by putting the resistors in series or in parallel. Putting them in series increases their length, while in parallel would effectively increase the cross-sectional area.
Hello, my name is Reed Johnson. I will be covering the third part of the project. What is a semiconductor? Semiconductors have a conductivity of that between an insulator and a conductor. This is because semiconductors form covalent bonds. These bonds share electrons with the surrounding atoms in the lattice. Because this lattice is stable, it requires a minimum amount of energy to free electrons to allow for conduction of electricity. Common examples of semiconductors are silicon and germanium. What makes semiconductors so useful? Semiconductors are very easy to mix with impurities to control their conductivity. This makes them very useful in a wide range of electronic applications. Because of this, they are used in almost every electrical device worldwide, from computer chips to hard drives, and even found in solar panels. Band gaps. The valence band is the outermost shell of electrons that has all of its vacancies filled, so it cannot conduct electricity. The conduction band is the outermost shell of electrons that is partially full, so it has free electrons. Semiconductors typically have no electrons in their conduction bands, meaning that electrons cannot flow. If enough energy is applied, you can get an electron to jump from the full valence band into the empty conduction band, leaving a hole in the valence band. Holes carry a positive charge, so we use P to represent them, whereas electrons in the conduction band carry a negative charge, so we use an N to represent them. Intrinsic versus extrinsic semiconductors. Intrinsic semiconductors have no additives. They have equal p-values and n-values. They generally have a low conductivity that is heavily dependent on temperature. An example of this would be pure silicon or pure germanium. Extrinsic semiconductors, on the other hand, are impure, and they're created with a process known as doping, where you take pure silicon or pure germanium and you add impurities to it. Extrinsic semiconductors generally have a higher p-value or n-value depending on the doping process used. These are known as p-type semiconductors or n-type semiconductors. They generally have a higher conductivity. While still dependent on temperature, it's also dependent on the level of doping used. In order to get an n-type semiconductor, you would dope with phosphorus. In order to get a p-type semiconductor, you would dope with boron. LEDs, also known as light-emitting diodes. When electrons jump across the band gap, they release energy in the form of radio waves, given by the equation E equals hc over lambda, where lambda is the wavelength, h is Planck's constant, c is the speed of light in the vacuum, and E is the energy gap between the bands. Pure GaP versus pure GaAs. GaP stands for gallium phosphide. Gallium phosphide LEDs have a band gap of 2.4 electron volts. If we convert that to joules, we can plug it into our equation and find that lambda equals 555 nanometers. 555 nanometers is green visible light on the EM spectrum. Now, if we look at pure GaAs, which stands for pure gallium arsenide, we'll see that our band gap is only 1.42 electron volts. Again, we convert that to joules and we plug into our equation, and we find that we get 850 nanometers, which ends up being infrared light on the EM spectrum.
Hello, my name is Joe Riddell, and we are going to be talking about silicon as a semiconductor. First, let's talk about silicon at 300 Kelvin. At 300 Kelvin, silicon has an electron mobility of 1350 centimeters squared per volt seconds. It has a hole mobility of 480 centimeters squared per volt seconds, giving us an electron and hole concentration of 1 times 10 to the 10 per centimeters cubed. Then our conductivity is given by sigma, which stands for conductivity, equals our charge times the quantity of the electron concentration multiplied by the electron mobility plus the hole concentration multiplied by the hole mobility, which gave us a output of 2.93 times 10 to the negative 6. And our resistance can be calculated using R resistance equals our length over conductivity times area, which came to a total of 2.4 times 10 to the 7 ohms. Electron mobility of silicon at 700 Kelvin is 400 centimeters squared per volt second. Hole mobility is now 150 centimeters squared per volt second. Our electron and hole concentration is now 10 to the 16th per centimeters cubed. And the conductivity is now 0.88. Resistance is now 114 ohms. This has been calculated using, assuming that we're making a resistor that is 1 millimeter squared wide and 1 centimeter long. Now let's imagine we took that same silicon, but we've doped it with boron, which dope is the process of adding impurities to semiconductors to make them easier to control. So our P, which is our holes, is now 2 times 10 to the 19th per centimeter cubed. And our free electrons, we now have 5 centimeters per centimeter cubed. Our conductivity is now 160, and our resistance is 0.625 ohms, still using that same resistor, size resistor we have in the last calculations. Now let's examine it at 700 Kelvin. Our p-value stays pretty much the same, but our n value is now 5 times 10 to the 12th per centimeter cubed. Our conductivity is lowered to 48, and our resistance has increased to 2.1 ohms.